You know, before a battery ever actually powers your car or keeps your lights on during a winter blackout, it begins its life as a wet, sloppy paste.
A highly toxic paste, actually.
Right, highly toxic. And I think that's the perfect place to start. Welcome to this deep dive. We are skipping the pleasantries today because we have a lot of ground to cover.
We really do.
So we're exploring this fascinating 2026 essay. It's a multi-source synthesis called The Node Learning to Remember Light.
That's a great title.
It really is. And it pulls from this breakthrough study in Nature Energy, plus some really heavy reports from the International Energy Agency and the Department of Energy.
Yeah, the IEA and DOE data really ground the whole thing in reality.
Exactly. And our mission today, well, we aren't just going to talk about battery chemistry. We are exploring a complete manufacturing revolution, specifically dry electrodes.
Which sounds a bit dry, no pun intended, but it's huge.
It is. We're going to dive into some wild speculation on how taking the wetness out of battery factories might literally decentralize global power grids.
And completely reshape energy economics along the way.
Right. Changing what actually happens when the power grid fails. So, okay, let's unpack this.
Let's do it.
We always picture energy storage as this sleek, pristine technology, like a monolithic battery wall in your garage or the sealed rectangle inside your phone.
But the factory floor is completely different. The current state of manufacturing lithium-ion batteries is heavily dependent on liquids.
Which is so counterintuitive.
It is. The active materials, the lithium, nickel, graphite, and the binders that glue them together, they all get dumped into this massive vat of solvent.
And it's not just water, right? It's bad stuff.
Oh, it's terrible. It's typically N-methyl-2-pyrrolidone, or NMP.
Okay.
It's highly toxic.
Right.
And they churn it in these giant planetary mixers until it becomes this thick slurry. And the only reason they do that, literally the only purpose of this toxic liquid, is just to get the dry powders to spread evenly across a sheet of metal foil.
I was reading the Department of Energy's breakdown on this, and it just struck me as an incredibly brute force way to build something. Oh, absolutely.
Because what you actually want in the battery is a perfectly dry, micron-thin layer of powder on a metal sheet.
Yes. But dry powder is famously difficult to spread evenly at high speeds. It clumps up.
So the industry solution is to just turn it into paint. You paint the foil with this wet, toxic slurry. But then you have a massive problem because you can't put a wet electrode into a battery.
No, if you did that, the solvent would react with the battery's electrolyte. It would create gas and basically destroy the cell instantly.
So you have to forcefully remove all that liquid you just added? And that removal is where the whole process hits a wall. The coated foil has to go into a drying oven. And we aren't talking about something the size of a pizza oven.
No, the sources talk about gigafactories where the drying lines are the length of a football field.
Exactly, just massive tunnels bombarding the wet foil with intense heat to evaporate that NMP solvent.
I was thinking about this and I came up with an analogy. It's like, imagine you want to manufacture a simple, dry, fluffy cotton towel. But the only way you know how to build it is to weave the cotton entirely underwater, inside this giant, sprawling, multi-million-dollar indoor water park.
That is, wow, yeah.
And then, because the towel has to be dry to actually use it, you build a massive array of industrial blast furnaces just to boil away the entire water park.
While also making sure you trap all the steam so you don't poison the town next door.
Exactly. You have to run vapor recovery systems to catch all the toxic steam. It's an insane way to make a dry towel.
It really is an insane architecture. And your analogy points right to the sheer inefficiency of the capital expenditure here.
Because you're spending all this money managing a liquid that doesn't store a single electron.
Exactly. The drying process alone is the single largest energy consumer in a battery cell factory. It's almost half of the total energy used.
Just to bake off the liquid.
Right. And because that NMP solvent is volatile and toxic, you need immense solvent recovery systems. You capture the gas, condense it back into a liquid, purify it, reuse it.
Which takes up a massive physical footprint.
The air handlers, the scrubbers, the heat exchangers, it's relentless electricity consumption. The source essay calls this the quiet burden of the energy transition.
The quiet burden? Because we all obsess over the battery's range or how fast it charges, right?
Yeah, the consumer metrics.
But we completely ignore the factory itself. If building that battery requires the land mass of a small town and the energy of a heavy industrial smelter, you are bottlenecking the whole global supply.
You're capping how fast society can transition. The essay points out that the finished electrode is this paper-thin marvel. but the factory around it is colossal and rigid.
You can't just put one of these factories anywhere.
No, you need huge grid connections just to power the ovens, and that centralization means we're going to struggle to meet global demand.
And the International Energy Agency says that demand is hitting 1,500 gigawatts by 2030.
Which is a staggering amount of storage.
So if the wetness is the bottleneck holding back the global battery supply, how do we skip the slurry?
Well, that's where the 2026 Nature Energy study comes in. The industry has been chasing dry electrodes for years, but this Zhang study is a massive paradigm shift.
Because they finally bypassed the wet part entirely.
Right. The theory is elegant. Just take the dry powders, the active material, the carbon, the binder, and press them together.
But doing that at scale is a nightmare, right?
It's unforgiving. Without a liquid, powders want to clump together. They generate static. They make brittle electrodes with dead zones where electrons just can't flow.
Because they don't mix uniformly.
Exactly. Powder rheology is just inherently chaotic. But the Zhang team solved it. And they didn't do it by inventing a new chemical.
He did it mechanically?
Yes. They altered the mechanical architecture. They looked at the binder, which is polytetrafluoroethylene, or PTFE.
Which is just a dry powder normally.
Normally, yes. But they found that if you apply specific, calculated shear forces, intense mechanical rubbing, and pressure, the PTFE particles fibrilize.
Okay, fibrilize, meaning what exactly?
They stretch out. They go from being these tight little spheres into these microscopic, spiderweb-like fibers.
Oh, wow. So instead of using a liquid glue, they use physical force to weave a microscopic net out of the binder.
Exactly. A three-dimensional net. And the active battery powders get trapped inside this web.
The essay calls this the architecture of touch, which is such a poetic way to describe battery physics.
It's a great description. What's fascinating here is that in a wet electrode, when the solvent evaporates, it leaves behind this random, somewhat porous structure.
Because the liquid had to escape, so it leaves little tunnels.
Right. But in this dry process, the fibrous carbon and the PTFE are mechanically locked together. It's highly ordered and incredibly dense. No evaporation means no microscopic pores.
Okay, I want to play devil's advocate for a second.
Sure, go ahead.
I get that a smaller, cheaper factory is great for the CEO of the battery company, but as a consumer, driving an electric car or powering my house, why should I care if my battery was baked in an oven or pressed dry?
Because of the performance leap. The numbers in the Nature Energy paper are wild. A standard wet process electrode tops out at around maybe 90 or 95% active material.
And the rest is just dead weight.
Yeah, binders and additives just holding together. But the Zhang study hit over 99% active material.
Wait, really? 99%?
Yes. And in electrochemistry, a 4% jump isn't incremental. It's massive. Every bit of non-active material is a penalty on your energy density.
So they packed way more power into the same physical space.
Exactly. And the architecture of touch gives it incredible stability. These dry-pressed pouch cells retain 78% of their capacity after 1,000 deep charge cycles.
1,000 cycles, even at high voltages?
Yes, even operating at high voltages, which usually degrades liquid-made electrodes really fast.
So it's not just a cheaper manufacturing trick, it's a fundamentally better battery.
Exactly. And here's where it gets really interesting.
Okay.
When you lower the barrier to manufacturing these better batteries, you don't just change the battery industry, you alter the macroeconomic landscape of energy itself. You redefine the edge of the grid.
The edge of the grid. Let's dig into that because the essay spends a lot of time on this concept.
It does. And it forces us to look at our infrastructure in a totally new way.
I like to think of the traditional grid like a giant heart pumping blood all the way down to the fingertips.
That's a good visual.
You've got this massive heart, a coal plant, a nuclear facility, and it pumps power out at high voltages through these main arteries.
Down into the distribution lines.
Right, the capillaries. And the fingertips are our homes, our schools, the hospitals. They are the edge of the grid.
But in the 20th century model, those fingertips are completely passive.
They just consume whatever blood gets pumped to them.
Right. The whole system is a one-way street. And the fundamental flaw is that electricity has to be consumed the exact microsecond it's generated.
Because the traditional grid has basically zero storage.
Zero. If the central heart trips offline, or a main artery gets severed by a wildfire or a fallen tree, the fingertips die instantly.
And we tend to treat blackouts like they're just unavoidable acts of nature. But the text argues they're actually structural failures of a really archaic design.
Oh, totally. The cascading effects of this are terrifying now. A blackout isn't just a romantic evening reading by candlelight anymore.
No, look at the Texas heat waves. A grid failure there means lethal indoor temperatures.
Or the East Coast deep freezes where pipes burst and people get hypothermia in their own living room.
Elevators trapping people, medical devices at home running out of their tiny backup batteries. It's life or death.
And our environment is actively rebelling against this centralized setup. Extreme weather is exposing how fragile long-distance transmission lines really are.
Plus, we are trying to add all this solar and wind power to the grid, which is great, but it introduces intermittency.
Right. You can throttle a coal plant up and down. You can't tell the sun to shine harder at 7 p.m. when everyone gets home.
Right. Solar peaks at noon, but demand peaks in the evening.
Sometimes grid operators literally have to turn off solar farms because they're making too much power at the wrong time and there's nowhere to put it.
It's a logistical nightmare. The grid is buckling. So if dry electrodes make battery factories smaller, cheaper, and cleaner, how does that actually fix the vulnerability of the fingertips?
By turning batteries into what the sources call timing devices.
Timing devices. I love that phrasing.
It decouples the creation of power from the consumption of power.
Right.
If your solar panels make extra power at noon, the battery stores that temporal surplus and you use it at 8 p.m.
Making electricity less instantly perishable.
Yes. And to hit that IEA target of 1,500 gigawatts,
Yeah.
storage can't just be massive utility-owned warehouses. It has to move to the edge.
Which brings up the internet analogy from the essay.
Yes, the parallel between energy and computing.
Right. So back in the day, computers were just these massive mainframes, and the edge devices were just dumb terminals.
Keyboards and screens with no actual processing power of their own.
Exactly. If the mainframe crashed, every terminal became a useless paperweight. But then processing power shrank, got cheaper, and moved to the edge. We got PCs, then smartphones.
The network became a distributed web of autonomous nodes.
Right. The internet was literally built so that if a data hub in New York gets destroyed, your email just routes around it through Chicago or Atlanta. So the essay asks, can the power grid become the internet?
It's a provocative question.
Mm-hmm.
But we have to be careful with the analogy because electricity is not information.
You can't email a kilowatt.
Exactly. You can't ride an electron around the globe. Electrons face physical resistance. They generate heat. You have to match voltage and frequency perfectly or things explode.
Kirchhoff's laws. The current is going to follow the path of least resistance on the physical copper that's right there.
Right. But the architectural rhyme still holds true. A system totally transforms when its edges become capable of doing more.
So what does a connected edge with memory actually look like in reality?
It looks like distributed resilience. Think about islanding.
Islanding, meaning disconnecting from the main grid.
Yes. Right now, if a tree takes down the power line to your neighborhood, your solar panels have to shut off immediately.
Wait, really? Even if the sun is shining?
Yes. It's a safety protocol. If your panels push power back onto the deadlines, it could electrocute the repair crews working on them.
Oh, wow. I bet that makes people who bought solar panels furious. They think they're independent.
Oh, it happens all the time. But if your house has a dry electrode battery and a smart inverter, it can physically disconnect or island itself from the dead grid.
It forms its own microgrid.
Exactly. The local solar charges the local battery, and the battery acts as a grid-forming asset. It generates that perfect 60 hertz frequency your fridge needs to keep running.
So the macrogrid collapses, but your microgrid is perfectly fine. The essay calls this holding its own daylight.
Holding its own daylight. It's a beautiful concept.
It captures the midday sun and unpacks it at midnight. But let's speculate a bit, because the essay goes way beyond just one house surviving a storm.
Right. It looks at the aggregate power.
Right.
What happens when you network thousands of these nodes together?
Virtual power plants.
VPPs. Yes. This is where the internet analogy becomes real. Imagine 10,000 homes in a city all have these cheap, dry electrode batteries.
Okay.
They don't just sit there waiting for a hurricane. Through smart contracts and software, those batteries act as one massive, decentralized power plant.
So on a brutal August afternoon, when everyone's AC is blasting and the grid is about to fail,
The grid operator doesn't panic and turn on an incredibly dirty coal or gas peaker plant. Instead, the software signals those 10,000 home batteries to each discharge just a tiny fraction of their stored power back into the grid.
boom, the demand spike is smoothed out instantly.
And the grid operator pays the homeowners for that power. The grid becomes an exchange layer. Neighbors are basically trading energy and backing each other up.
I mean, that sounds like a utopian dream. Clean, perfectly resilient, decentralized power. nobody ever loses power again.
It does sound utopian.
But, and this is a huge but, moving from a laboratory breakthrough in dry electrodes to a revolutionized society isn't a straight line.
No, it's not.
So what does this all mean for people who can't afford a $20,000 battery system today? Because right now, energy sovereignty is absolutely a luxury product.
And that is the defining risk here. The essay warns about a future of rugged individualism with lithium cells.
Energy gentrification.
Exactly. If manufacturing stays expensive and centralized, only wealthy people will buy these systems. They'll retreat into gated communities, slap massive solar arrays and batteries on their mansions, and effectively secede from the public grid.
They basically buy immunity from climate change and grid failures.
While everyone else, apartment renters, lower-income neighborhoods, rural towns, gets left tethered to a decaying, fragile, centralized grid.
And as the wealthy leave, the utilities lose their best-paying customers, which leads to the utility death spiral, right?
Yeah. Yes. The fixed costs of maintaining the poles, the wires, the power plants, that massive financial burden falls onto a shrinking pool of ratepayers who are the least able to afford it.
So power bills skyrocket for low-income families, and the service just gets worse and worse.
It's a nightmare scenario. And that is exactly why democratizing storage is so critical. This dry electrode breakthrough is an economic lever.
Because if you eliminate those massive drying ovens and you shrink the factory, the cost of the battery plummet.
Right. And when the hardware gets cheap enough, it stops being a luxury good and becomes basic civic infrastructure.
Like public housing basements being retrofitted with massive battery banks that the city pays for.
Exactly. Or rural communities that currently rely on expensive, dirty diesel generators during outages, they could finally swap those out for silent, clean community batteries.
The grid doesn't disappear. It just changes its purpose. It becomes a backup for the local nodes instead of being the only lifeline.
The transition isn't just about swapping coal for solar. It's about changing who owns the backup power and where it physically lives.
But the author issues a really harsh reality check here, which I think we need to talk about. Simply inventing a clean technology doesn't magically create a just society.
That's a crucial distinction. Technology does not distribute its own benefits.
A breakthrough in PTFE fibrillization doesn't draft the municipal policy for a virtual power plant.
No. And it doesn't solve the massive geopolitical nightmare of mining the lithium and nickel, or the recycling infrastructure we are going to need in 10 years to prevent a mountain of toxic e-waste.
And even just getting the dry electrodes out of the lab is hard. The sources from Fraunhofer and energy storage materials highlight the valley of death for hardware scaling.
Right. It's one thing to use sheer force in a pristine lab. Doing it continuously in a massive gigafactory means dealing with calendaring and extrusion.
Tell me about calendaring. That sounds intense.
It is. You're feeding this dry powder mixture through a series of massive, heated, high-pressure steel rollers.
Just crushing it into a film.
Crushing it to induce that sheer force, creating the PTFE web on the fly. And extrusion is using these massive twin-screw mechanisms to churn the dry stuff under immense pressure and push it through a die.
The engineering tolerances there must be absolutely microscopic.
They are unforgiving. You're pressing a film that's maybe 50 microns thick. If the powder flow ability is off by a fraction of a percent, or a steel roller deflects by a hair under the pressure,
the whole electrode is ruined.
Yes. The web tension has to be flawless, or the film just snaps as it moves down the line.
Whereas the wet slurry, as terrible as it is, naturally smooths out those imperfections because it's a liquid.
Exactly. The industry has 30 years of experience optimizing wet slurry. Dry processing forces engineers to solve fluid dynamics problems without any fluid.
That is wild. So we have this superior architecture, but it's incredibly hard to build at scale, and it's wrapped up in all these socioeconomic policy fights.
Yes. But, and this is the hopeful part of the essay, overcoming these manufacturing hurdles, changes what is realistically possible.
It lowers the financial wall.
Exactly. It makes putting batteries in public housing a realistic municipal debate, rather than an impossible fantasy. It alters our baseline expectations for civic life.
The text has this beautiful phrasing. It says the goal isn't to make storage glamorous. The goal is to make it ordinary.
Ordinary. That's the perfect word for it.
Because we rely on invisible civic infrastructure every single day. The water mains under our streets, fire hydrants, sewers.
We walk right past them without a second thought.
Right. They're vital, but totally unremarkable. And the ultimate triumph of this dry electrode breakthrough will be when it becomes invisible.
Picture a Category 5 storm hitting the coast. It takes down the high-voltage transmission lines. The main grid goes dark.
And there's absolutely no panic.
None. The neighborhoods seamlessly island themselves. The local batteries take over the load, perfectly mimicking this 60 hertz frequency.
The medical equipment at the clinic just keeps running. Refrigerators stay cold. The catastrophe is downgraded to just a bad weather day.
The resilience becomes so perfectly ordinary that people actually forget how fragile the old system used to be.
Man, what a journey this has been. We started deep in the mud of the wet factory floor. Toxic NMP solvents, massive planetary mixers, drying ovens the length of a football field.
And we traced how drying out that process, forcing powders to bind through shear force and microscopic PTFE webs, gets us an electrode with 99% active material.
Which scales up to enable the 1,500 gigawatts of storage we so desperately need. And that rewires the global power grid, turning passive, vulnerable fingertips into active, resilient nodes holding their own daylight.
The chain of causality from a chemistry lab to the macroeconomy is just profound.
It really is. And I want to leave you with one final provocative thought that builds on the essay's title, Learning to Remember Light.
It's a very philosophical thread.
Because if you think about it, human history has always been dictated by the immediate availability of nature.
We're entirely reactionary.
Right. We seek shelter when it rains. We sleep when it gets dark. We freeze if the fire runs out of wood. Our whole infrastructure is just a real-time reaction to whatever the atmosphere is doing.
And the centralized power grid didn't actually fix that. It just moved the vulnerability 100 miles away. If the coal plant stopped burning, the lights went out in your living room in real time.
Exactly. We've always been at the mercy of the weather's timing. But what happens to the human psyche when a community's infrastructure develops a memory?
That's the real shift.
When every single home, every hospital, and every school has the physical capacity to store a calm, sunny Tuesday and then unpack it during a violent, stormy Friday.
We completely decouple our localized survival from the immediate whims of nature.
If a neighborhood is no longer afraid of the dark and no longer terrified of a centralized lifeline failing, the baseline anxiety of modern living fundamentally changes.
It's not just an engineering transition anymore. It's absolute localized energy security.
It changes our relationship with time and nature itself, providing a structural peace of mind we've basically never experienced in human history.
Transitioning from a society that simply consumes power in a panic to a society that remembers light. It's one of the greatest evolutionary steps we could take.
Building the capacity to weather the 21st century, not with rigid, massive fortresses, but with a distributed, adaptable web built out of dry powder. It's an incredible paradigm shift. Thank you for coming along on this deep dive with us. The next time you look at a power outlet in your wall, or you hear the hum of your refrigerator, I hope you consider the invisible architecture making it all possible. Think about the massive factories boiling away solvents today and the quiet, dry-pressed nodes of tomorrow. Think about what your own neighborhood will look like when those dumb wires finally learn how to hold their own daylight.